Try just to keep your image. Okay. Okay. So let's see. We were in the middle of trying to discuss boosting in the context of, I mean, I'm certain all of you are familiar with boosting, but I'm trying to talk about it in a context that you're less familiar with, which is a PAC learning or the formal theory of learning, because I thought it would be useful. And so last time we were kind of setting up the ground for the discussion of boosting. And I want to still not get to boosting yet. I want to today take an example, so we will. I think it will be helpful for us to better understand the concept of PAC learning, and then it will be easier to understand the boosting I want to talk about. So just to remind us, PAC learning means that so we have two parameters that control this, which is epsilon and the delta. The delta is the chance that, in spite of the fact that we get enough samples, this is m is the number of samples, we are not going to succeed in learning. And learning means that the average loss on the distribution that was chosen is going to be less than epsilon, plus a corrective measure, because why is that corrective measure appearing, this mean mean loss on the hypothesis set? Because we can't be expected to do better than the best hypothesis in the hypothesis set, because we are choosing a function from the hypothesis set. So the learning algorithm is choosing a function from the hypothesis set. So we can't accept to have a loss that is better than, than that. And typically, if the hypothesis set is H is rich enough, then this number is very small. Like, for instance, for neural network could approximate any function more or less. So this number will be very small. Now, the other thing is that so M needs to be not within some boundaries. You'll see things of this flavor, like smaller than or bigger than something that is dependent on the more you want to drive the loss as small as possible, the more data you would need. And if you want the chance of making a mistake to be smaller, the more data you would need. And then the complexity of the hypothesis set determines how much data you need. And if it's finite, then you just get its size. But then if it's not finite, you get, like, for instance, for even for logistic regression, it will not be finite, because it has infinite parameters, right? Parameters of type real number. So once it's not finite, the hypothesis set, because it's all the hyperplanes, for instance, or whatever, then there's another theory that attributes a complexity to the hypothesis set. If that it's called the VC dimension. If that complexity is finite, then you can learn, otherwise you can't. So you don't want the hypothesis set to be too complex. We've seen that with the you know we've seen that with the bias and precision trade-off. Like if the we've seen that with you can use any polynomial of degree 1, 2, 3, then as your hypothesis set. So if the polynomial is of degree 2 big, then you start picking up noises. So you don't want the hypothesis set to be too complex, but not but expressive enough to have some good candidate for the learning. Otherwise, the loss will be very big. So there's a trade-off here. Now, another concept here is the ERM, which means that I'm looking at the training set that I'm picking at the endpoints, and I'm taking the hypothesis set that is best for that case, for the endpoints that I've sampled. If it's a finite set, the hypothesis set, then it's a finite procedure to identify that particular hypothesis that will give you the best result. So what I want to do now is I want to give you an example of all of this. Any questions or comments up to now?
No, not for me.
Okay. Okay, so let's have a look here. Let's take a very simple example. So assume we're looking at just at a one-dimension learning problem. Very simple. Okay, this is just the real numbers, and the hypothesis set is that we have a point A, and all of the points above it, the classification problem, are pluses, and all of the process points below it are minuses. So the hypothesis set is just, it has all the numbers, all of the numbers in that's the hypothesis. Okay, and we assume that we assume what's it called, the realizability assumption. So we assume there's some point that we don't know in H, which is the point that is chosen for the learn. Okay, so here's a concrete hypothesis set, very simple. We have a classification problem, and here is the function, and the The distribution could be any distribution, but we assume that there's this a one point that is the thing we're trying to learn that divides R, and we want to find it. Okay. Now we pick up like 20 points. I don't know, not 20, like we get these points, okay? 7 points. Is that possible? Can we get something like that in the sample? So this is our sample. M is equal to 7. Now the question is that possible? Can we get something like that? The answer is either yes or no.
No, it's not possible.
Very good. Why not?
Because all the pluses and must be in the same side.
Right.
And here, yeah, and here
because
we have
of the,
minuses in the middle.
Exactly, Gomer. Because of the realizability assumption, we can only see pictures like that: minus, 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 and then possibly plus. No, plus. That's the only possible pictures, right? This picture is not possible. Can't see it because we made the realizability assumption. Okay, so you got 7 points like this, okay? So what's going to be your solution? Give me an algorithm. What's going to be the A that you're going to return? And how are you going to choose it? You can do it in 2 stages. Where is A going to should fall? Can you tell me that?
Maybe between the right minus and the left plus.
Exactly. So A should fall somewhere here. Okay? This is a good A. Well, any A here in this, in this interval is a reasonable A, according to the data that we see. And then for any point that is less than A, will return minus. For any point that is bigger than A, will return plus. Okay? Now, how can you choose A? Give me an algorithm.
But Eitan, there are many options to choose A.
Okay, so give me an
For
algorithm.
example, I can take it as the average point between the
Minimum
closest plus and minus, but I'm not sure if it is good enough. I can think
it's
about 10
as
algorithms.
good as you know, Liran. It's as good as you know. Okay.
Yeah.
Okay. So for instance, we could take the minimum of the pluses and the maximum of the minuses, which is efficient. You can do it quickly, and then choose something in between, either randomly or choose the average, like Eliran was saying. That will be an A. Now, any such A is an ERM because it gives you the best result on on the sample set, which is 0 mistakes, right? So any A in this range, less than the minimal plus and more than the maximum minus, will give you an ERM algorithm, because it's going to be making the minimum mistakes on the sample set. This is the sample set, which is 0 in that case. Okay. Now, if there is a probability of getting here, which is high, then we're still going to have a high chance of making a mistake, right? If the probability between here and here of the probability that was chosen, remember the probability is chosen for us, we are not choosing it. So if the probability here is big, then we're not in good shape, right?
Yeah.
Does that make sense?
Yeah.
So the question the agnostic PAC learning is asking us is how many points do we need to get so that the probability here in this range is going to be small. That's the point. Okay. And so intuitively, if the probability, if you get more and more points, then it will be more and more representative, right? So if we have here a gap, then the probability of the gap is smaller and smaller and smaller, right? That's the intuition. So the more points I get, the more accurate my A is going to be. And the gap that is going to be left here is going to be is going to be small in terms of the probability, not its length. So it doesn't matter. The chance that I'll be making a mistake is going to be small. So basically, if we go back to the definition here, the M here is giving us, and those numbers here are giving us a way to do it quantitatively. So it's a way to choose how big the sample should be so that we're going to be happy here. And the probability in this range is going to be small, and our ERM is going to give a good result. Okay. So does that make sense now?
Yeah.
Yeah, but one question, maybe I missed it, but isn't it important where will be the A located? Because I understand that you said it is not, but I don't know, maybe if the data is drifted in some case. I need to think about a specific case, but I don't know.
So if you look here, this is very important. If you look here, let's look at the definition again in the context of your question, Ryan.
Okay.
And I want you to notice that there's no guarantee here with respect to drift. Okay? For all epsilon and delta and P, so an adversary is choosing some probability, blah, 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 blah. The loss function is less than, ignore this epsilon, on what probability space? The P probability space.
Mm-hmm.
So all of the classical techniques in machine learning don't guarantee anything in terms of drift to start with. They tell you that if you work with the same probability that you started with,
mm-hmm.
then it's going to behave well. Now it's even deeper than that, because the probability here, if you pay attention, is actually on x times y. Okay, which means it includes the conditional probability of getting one of the classes. So given a set of inputs X, you're not guaranteed to be given a certain class, but there's a probability distribution of getting each of the classes.
Yeah.
So even if the object, even if the function that you're trying to learn changes, even if the frequency of the object changes, or any of that, any such drift, whatever drift is, you need to define it, but whatever change you get in P, essentially, then, from the point of view of this definition, everything is off. There's no guarantee, nothing, okay? So this is an interesting point to notice. So you don't, from the point of view of this definition, what is learning guarantees you a behavior on the probability that you've used for sampling the data, and the probability includes the classification step. It's over the Cartesian product of the input and the classification step. So all sorts of drifts that you can imagine, most of them, and ones that you can't imagine in this framework, most of them would be a change in probability. And there's no guarantee that there's going to be anything here that is useful if the probability changes. Okay, outside of the model. But in practice, we know that always the probability changes. But that's a subject for another discussion and another meeting. Okay.
Okay.
Okay. Okay. Any other questions or comments? Okay, great. So I think I'm going to run us through another example next time, and then I'll feel comfortable that everyone understands what I'm talking about, and I'll talk about them. Okay? Okay. So yeah, thank you very much for joining, and we'll continue next time.
Thank you very much, Eitan.
Thanks,
Thank you.
Eitan.
Thank you, Eitan.
Right.
Bye-bye.